Now we're on to Chapter 4, Section 5, Formal Charges and Resonance. So in our last section, when we started drawing Lewis structures, I mentioned briefly the idea of resonance. Here we're going to work to use the idea of formal charge to determine what the most reasonable Lewis structure would be for a given molecule. Let's start with formal charge. Formal charge is a type of hypothetical charge that each atom would have based on the number of valence electrons they brought to the molecular structure and the number of valence electrons they have in the structure. So, for example, if you recall in the last section, I did the Lewis structure for CO2. And when I did it again for the second time at the end of the video using the need minus have concept, each atom needs 8 valence electrons. Carbon has 4, oxygen each have 6. I get 24 minus 16. That tells me I have 8. Divide by 2 because each bond has 2 electrons. So you'll recall we said we had 4 bonds. Now, when I did that, I quickly, in that video, just added a bond here and a bond here to make 2 double bonds. But we also know that there's a possibility of triple bonds. So why did I not give a structure like that? Well, let's finish both of these structures here by adding our lone pairs to fulfill every atom's octet. So you recall this oxygen needed 2 more lone pairs. This oxygen also needed 2 more. Now with this new structure here, this oxygen is going to need 3 lone pairs, and this oxygen is going to just need 2. So to determine formal charge, we're going to consider how many valence electrons the atom would have if it were a free atom, and then how many valence electrons it looks as though it has in the structure. So for example here, in our first Lewis structure, you can see that, so I know oxygen has 6 valence electrons, or brought 6 valence electrons to this structure, and you can see based on this drawing here that 1, 2, 3, 4, and then remember each bond accounts 1 valence electron from each atom. So that oxygen has 6, and so its formal charge would be 0. Carbon has 4 valence electrons as a free atom. Now, if I look at my structure here, each of these bonds accounts for 1 valence electron from carbon, so I have 4 minus 4, again, a formal charge of 0. And then back to this oxygen on the right, we're going to have the same idea here. 6 as a free atom, and then 1, 2, 3, 4, 5, 6 in this structure. So each of my atoms here has a formal charge of 0. That's the best scenario that we can have. That's what we're looking for in a neutral molecule like this. Obviously, if it were a polyatomic ion, I would expect it to have some overall charge. Some overall charge remained at the end. Now let's look at this other possible structure that I've drawn, and you can see what's going to happen here. So if I had, change my color here, if I took a look at this oxygen, again, the number of valence electrons in the free atom is still 6, but if I look at this structure, it appears as though this oxygen, 1, 2, 3, 4, 5, 6, has 7 valence electrons. So this oxygen has a formal charge of -1. Okay, this carbon over here has 1, 2, 3, 4, and so we know it starts with 4, it has 4, so it has a formal charge of 0. And finally, my right oxygen here, 1, 2, 3, 4, 5 valence electrons. Again, starts with 6, and this structure only has 5, so it has a formal charge of +1. Now, the good news here is that my charge cancels out and I don't have any overall charge on this molecule. So I would never want to be in a situation where my formal charges don't cancel out and I have something other than 0 for a neutral molecule like CO2. But the bad news is, if I can avoid formal charge, then that is what I want to do. So that means for us that this structure of carbon dioxide is much more favorable because it has no charge throughout the course of the molecule on each individual atom. This second possibility, you can see I have an oxygen with a -1 formal charge and another oxygen with a +1 formal charge. We would like to avoid that if possible, so we would not consider this structure to be a viable option for CO2. Let me do another one, and this time I'll pick a polyatomic ion. I'll do NO2 minus. Okay, so again, I'm going to do the need minus have start here, where each atom needs 8. Based on their location on the periodic table, that's how many each atom has. And then I cannot forget the charge here, so I get 1 additional electron. So 24, 18, this tells me I have 3 bonds. Okay, so now if we made our structure, nitrogen with 2 oxygens. Okay, I've used up 2 bonds. I determined I needed to have 3 bonds. So let me add a double bond here. Now let's complete all the octets by adding lone pairs. That gives me 8 for the left-hand oxygen. Currently the nitrogen has 6. There would be 8. And this oxygen has 4. And there is 8. Let me double check to make sure that my structure has the proper number of valence electrons. And I would see 2, 4, 6, 8, 10, 12, 14, 16, 18. So yes, this is a good Lewis structure for the NO2 minus ion. Here is where I have an example of resonance. I could have drawn this structure differently, and it would have still worked, and I still would have had the same overall charge and things like that. So actually, before I draw the structure a second way, let me go ahead and show you what I mean about formal charge here. So this oxygen, you can see I have 1, 2, 3, 4, 5, 6, 7 valence electrons. So I have a -1 formal charge. The nitrogen here has 1, 2, 3, 4, 5 valence electrons, which is the same as the amount of valence electrons the free nitrogen atom would have. So that has a formal charge of 0. And now my last oxygen has 1, 2, 3, 4, 5, 6. And it, as a free atom, has 6. So it has a 0 formal charge. You can see here, unlike the carbon dioxide, where I had formal charges that canceled each other out in a neutral molecule, this polyatomic ion that has an overall charge of -1, when my formal charges are added up, I still show that overall charge of -1. Okay, so now let's think about resonance. So again, if I were to consider this oxygen A and this oxygen B, you can see that I can switch what's happening to each oxygen here. So I could put the double bond on oxygen A with 2 lone pairs, and then leave the single bond on oxygen B with 3 lone pairs. Okay, so that is an example of a resonance structure. So you can draw the structure of the Lewis structure of the molecules different ways that are equally acceptable. In this case, it happens a lot with double bonds, as we've seen here. And then I just want to make sure I finish this off the correct way. I would put all the possible structures in brackets like this and indicate the charge outside of the bracket so that you know that there is a charge on this particular molecule. So when we're drawing our Lewis structures, we want to be checking formal charge and thinking of any possible resonance structures. to make sure that we include all of those in a correct Lewis structure for a particular molecule.